Hello, we are Team 28 for the Design for Manufacturing interim presentation. Today we will be discussing our analysis and redesign of a manual hand mixer for assembly. On our team, we have Kimia Baisa, Eleanor Frazee, Aaron Gunn, Tommy Vincent, Audrey Wong, and Benjamin Wong. So the manual hand mixer is a very versatile tool that's used for various applications from cooking to art. Its smaller size lends to versatility as well as maneuverability, since you don't need to worry about a power cord or having to reach an electric power source. It's a purely mechanical system that requires two hands to use, where the user turns a crank that ends up rotating whisks. The annual US manual hand mixer demand is around 50,000 devices, with a calculated annual growth rate of 5.5% in the forecast period of 2018 to 2028. Our primary customers for this device are at-home chefs or DIY artisans that aim to use this to create their own adhesives or maybe skincare products.
Seen is the exploded view of the assembly breakdown of our two-whisk variant of the hand mixer. As you can see, there are 11 distinct components which go into this assembly.
In our functional analysis, our team created a fast diagram with the main function of the hand mixer to mix food. We only had one main functive, which was to rotate the whisk attachment.
So we came up with two different assembly sequences. This is the first. We start with the whisk guide and proceed to build off of that with different components. We have a frame, which also has different subcomponents. Those two parts are put together to create the final assembly. For our second sequence, we start with the frame and its various subcomponents. And then we attach the whisk guide and its subcomponents to the frame. And then its respective covers go on. So for our sequence criterion table, we evaluated each of the following and determined that sequence 2 was slightly better than sequence 1. So we decided to pursue that one.
All right, utilizing our fast diagram as well as our assembly breakdown, we were able to create a functional component mapping matrix, which combines the two and determines which component performs what functive, as you can see here in our mapping matrix.
Next up, we have our bill of materials. This was estimated with 50,000 units per year, and the material costs were found from hubs.com, McMaster-Carr, customparts.net, and the product design for manufacturing and assembly chart used in the lecture slides. We opted for manual assembly and estimated the cost to be $19 an hour. Most of our components were machined, extruded, sheet metal formed, or injection molded, with the fasteners being purchased. This led to a total cost of $13.34. We then evaluated the functional importance and the manufacturing and assembly cost for all of the components. With this, we found that the gear lever knob, whisk base, whisk stem, and handle cover should be considered for elimination in the redesign as they have low functional importance. We decided to keep the whisk guide, ring gear, gear lever, and frame since they have low cost and high importance. And we finally are considering a redesign of the whisk gear, and ring gear cover for the final redesign as the cost is high, but the functional importance is also high.
Utilizing our fast diagram again, we were able to create a functional differentiation table where we examined what functives were used by what customer groups, with the main differentiation with the customer groups being the enhanced portability and homogenized items functives.
Looking at our component commonality table, as you can see, like from the functions from the fast diagram, they will all be performed by these platforms and modules. The modules of the design will be the whisk and the whisk holder. As you can see in our new product redesign, we have the new whisk base and the new whisk. We have switched the whisk to a beater so that it can homogenize items, as well as it's being holded by the whisk holder to make it a modular component.
Shown is the product family assembly diagram. It offers two separate sequences, the first sequence being built off of the whisk guides, and the second sequence being built off of the handle. As confirmed in the assembly sequence comparison table, sequence 2 is also more optimal for delayed differentiation, enabling reduced downstream assembly costs.
Thank you for listening to our presentation.